topic is about B tree. So why we have to go for B tree? In order to have searching mechanism more effectively, we have to go for B tree, because when binary tree and binary search tree, we can have only two children that can be connected to the parent. Now in B tree, it can be have n number of children. Let us consider what is B tree is. So the B tree of order M, which will be having a following structural property. So first one is a root can be a leaf node, or it can have two or m children. Similarly, a non-leaf node other than root can also have m by 2 to m children. So the difference is root will have minimum 2 children, but a non-leaf node should have minimum m by 2 children. So the symbol what is given over is a ceiling operation. So if you m is equal to 3, when you have perform m by 2, it is going to be 1.5. So we will not take it as a flooring, we will be taking it as ceiling. So if it is 1 point, means you will go for 2. Now the third rule is all the leaves must be in same depth, and all the inserted values will be stored only in leaf node. So the leaf node, how many nodes, how many values it can hold? It can hold also m by 2 to m values. So in this diagram, we will represent all the non-leaf node as a ellipse symbol and the leaf nodes as a rectangle. Now this is an example for the given diagram. So you can see the diagram which is given here is the top two most level is the level 0 and level 1 are going to be the non-leaf node, and leaf nodes are at the bottom. You can see this is an B tree of order m is equal to 4. So it can have minimum 2 elements and maximum 4 elements. So examples are given here. So the non-leaf node will be of structure like it will have m pointers and m minus 1 search key values. So what do you mean by search key values? So if you see the root node, you have 3 search key values, 21, 48 and 72. So it is m is equal to 4, so you have 4 pointers. The first pointer will refer to the nodes that are less than the search key value 21. The second node will refer to the child which is greater than or equal to 21 and less than or 48. The third child will be greater than or equal to 48 but less than 72. Whichever is greater than or equal to 72 will go to the last child. So this is how the searching and insertion will happen. So usually we have two types of popular B trees are here. One is if m is equal to 4, then you will be calling it as a 2, 3, 4 tree. If m is equal to 3, then we call that B tree as 2, 3 tree. The worst complexity is the time taken for insertion and delete operation will be of nearly O of log n. So because it has to search through all the non-leaf node, then it has to go for leaf node. After deletion also it has to satisfy the property. So it takes nearly O of log n. So the most legal choice for choosing a B tree is with the order m is equal to 3 or m is equal to 4. That will be the most efficient one. So where do we mostly use B tree? So B tree's application will be in database systems, that is DBMS. B tree will be used as an index for many physical disks that are connected to the system. So it acts as a directory services. The only drawback you will have here is a disk access overhead, because the time taken for the disk to move and find to the appropriate location to read or write a perform operation, it will take O of log m time. So that is why it is considered as inconsequential. So as long as we will try to use B tree if it is needed. So let us consider how B tree is going to be constructed for m is equal to 3. So first we will write the rule. So B tree of m is equal to 3. So what is the first rule is? The first rule, the root can have 2 to 3 children. Okay. So it can have 2 to 3 children, and the non-leaf nodes also can have 2 to 3 children. Now how many nodes you can have in leaf? How many elements can be stored in leaf? Leaf can hold 2 to 3 values. Okay, then fourth rule is all the leaves should be in same depth. All the leaves are in same depth. So with these 3 rules in mind, we will try to solve this problem. We will do one by one. So let us insert 22. Okay, so I am going to perform insert 22, 8 and 11. So first, when 22 is inserted, so a leaf node can have 3 nodes, so I will have 22. So next for the insert 8, So it is going to have 8 and 22. So you can see here the elements in leaf node will be in sorted manner, okay. So keep that in mind, it is always in sorted manner. So when I insert 11, so it will become 8, 22 and 11. Now the next element to be inserted is 41. So for insert 41, so you can see 41 will be inserted over here. I don't have space, so what happens is this node will be splitted into two nodes. So I will split into two nodes. So one will be 8 and 22, the other one will be 11 and 41. So 41 alone will be here. It will request one node for its existence, so it will access one and that. Now you can see I have two leaf nodes. So here everything is a root node, but I said root can be also a leaf node. So this is a root node, but now here you can see, if you consider this is a root and this is a root, I have two B trees, so I have to move. So now I create a non-leaf node and I am having these two nodes as a two child, because a node can exist with minimum two child. Now what will be the search key value for this node? So always the second child's first value in the leaf node we will take it. So you will have 11 dash. Why dash? We don't have third child, so it is 11 dash. So the next element to be inserted is, I'm going to insert 52. So you can see it is greater than 11, so it comes to second child. I have a space, so 52 will be stored over here. Now when I try to insert 31, so 31 will be tried to insert over here, where I don't have a space. So what I do, I will split the nodes. Okay, now 52 is to be inserted, so we will split. We made a small mistake in the previous one. We'll see here, I didn't sort the elements. So when 11 is inserted, it should be sorted, but I didn't sort it. So if it is sorted, it will be 8, 11, 22. So 8 and 11 will be separate and 22 and 41 will be separate. So then you will have this diagram. So you will insert 52. When 31 is inserted, it will be inserted in the middle between 22 and 32. So we will have a split. Now this node, a non-leaf node, it can have maximum 3 children. So I can have the new node connected to it. Now we will update what is the search key value. So the second child's first value is 22. So you will have 22 dash. Then the third child value is 41. So what do you mean by that? Less than 22 will go to first child. Greater than or equal to 22 and less than 41 will come to second child. And greater than or equal to 41 will go to third child. So the next element to be inserted is, which is going to be 17. So where 17 will be inserted, it is less than 22, so it comes to first child. So 17 will be inserted over here. The next element to be inserted is 16. So I will try to insert 16. It is less than, it comes over here. I don't have space. So what happens? This node will be splitted. So what happens is, if you split it, you will have 8 and 11 will be separate node. You will have 16 and 17 as a separate node, right? So the rest of the node is 22, 31, and it is 41, 52. So this node, it is already with it is connected to the 22, 44 one. Now if you try to connect the new child, it becomes 4 childs. So 4 child, a node can, and a non-leaf node can have maximum only 3 childs. So what happens is, I cannot connect over here the new node. Okay, new node cannot be connected over here. So what I do is, I create a new non-leaf node for this node, and the second child first value is 16. So I will update here is 16 dash. Similarly here only 2 childs, so I will replace it with 41 dash. Now all the leaves should be in same depth. So what happens is, these two trees will be connected with a root node with this. Now considering this as a left subtree, the entire left subtree must be considered. So you have to consider it as this entire structure as a left subtree for the, that is the second child for this node, and the starting value is 22. So you will have 22 dash over here. So it will be the 22 dash. So the next element to be inserted is, we can insert 23 and 61. So we'll see where 23 can be inserted. Greater than 22, less than 41, so it comes over here. So you will have 23 over here, 23 and 31. and for 61 it is greater than 22, greater than 41, so it comes over to the last child, so it will be 61 over here. So this is the diagram for inserting. Now when I try to insert 58, so 58 will be inserted over here. So what happens, you will split a new node, so you will have 58 and 61 together here, because it will 61 will come over to this place, so 61 will be here. Now this child is divided into two childs, so we have to check whether the third child can be connected. Yes, it can be connected, so we will update the child as 41-58. So we will see the next element to be inserted. It is 59. It can be inserted over here, so it can be inserted over here, 59. So I'll rub this. So what happens is 59 will be inserted here. So 59 is inserted here. So we'll see the next element to be inserted is 12. So you can see 12 can be inserted over here. So I can insert, I have a space over here, so 12 will be inserted here. So the next element to be inserted is 1. You can see I can have a split over here for the insertion 1. So we'll see how split happens here. So we'll see where 51 will be inserted. So 1 has to be inserted over here. So what happens is first I will create a new node. So I will put 1 over here, then I will borrow 8. So I will borrow 8. Now this child is removed. Whether these two child can be accommodated with this non-leaf node, yes, it can be. So we will just connect and we will update the value. Now the second child first value is 11. So you will have 11 dash and 16. So the next element to be inserted is 18. So 18 can be inserted over here. So I will insert, you have a space for another element. So 18 is inserted over here. Right. The next element to be inserted is 19. So where 19 has to be inserted. So insertion of 19, you can see 19 has to be inserted over here. So the node does not have a space. So we have to split. So if you split, it will become 16, 17 and 18 and 19. So now this child cannot be accommodated by this node. So what I have to do? We'll see it shortly. So after splitting, you can see 16 and 19. If you try to connect it, it will have 4 childs, so it cannot be connected. So what I will do is I will create a new node. So I will create a new node and I will connect this. So I will update this term and this term. So if you update it, this will become 11 dash and this will be 18 dash. Whether this node can be accommodated with the previous node, yes, it can be accommodated. So now if you update it, it will become 16-22. So because you can see 16 most and 22 most is the second child's leftmost and third child's leftmost value. So next insertion is about 18, 19 is done. Now the last insertion is insert 28. So where it will be inserted? It will be inserted over here again. So you don't have a space. So this node will be splitted up into 22 and 23. Then you will have 28 and 31. So these two nodes, it cannot be accommodated, cannot be attached to the second node. So this node, okay, this is second node. So it cannot be attached. So what we will do? We will see it shortly. We'll change in the next slide. I'll draw it. So we have drawn the diagram. So if I try to connect these two childs to this node, it cannot be done since it is having 4 childs, so you can't connect it. So what I do is I will try to form a new node and I will connect. So this will be 28-31. So if I try to connect with the root node, again root node is having more than 4 childs. So what we will do is we will remove this entirely. We will form a new node, interior level, next level of nodes. So I have to form this node. So it will be 16 dash and this will be 41 dash and this you will get updated. Only 2 child is there, so you will have 58 dash. So now these two are connected. Now this final thing will be connected with the root node, so the value will be 22 dash. So this is the creation of construction of binary B tree of order m is equal to 3. So now let us see the delete. So let me delete 58 first. So searching from 22 greater, 41 greater, 58 it is equal, so it comes over here. So when 58 is deleted, automatically, so when 58 is deleted, so here it will get updated as 59 dash. So this is for insert 58. Now when you delete 12, what happens is this node's existence will not be possible. So what happens, 11 will try to be occupied over here. So we'll see it in the next slide how it is done. So when 11 is deleted, 12 will occupy with the 198 node, so it will get combined. So when it combines, there is no possibility of this node, so you can't have this node. So what happens is I will try to combine over here. Now when this is combined, this node existence also will not be possible, so you will remove this. So ultimately this node also will be removed. So what happens is this node and this node will not be get connected, and the root node will be removed. Okay, so this node also will be removed. Okay, so what happens is the tree will have only one node, and that will be of with this 3 nodes. So it will be 22-41. So this is the final diagram after delete 11. So let us now delete 12. So what happens is 12 will be deleted, right? Now every leaf node is having only 2 nodes. If I try to delete anything, it will just replace it. So let me delete 31. So what happens if 31 is deleted, 28 will get occupied to the next node. So now if 31 is deleted, so what happens is 28 will go to 22, 23. Now it is occupied. Now if it happens, the existence of this node is not possible because you have only one child will be connected. So you will remove that child. So that child will be removed. Then it can be accommodated over here. Now the root node is with only 2 childs, so we'll update the value. So it will be 22 dash alone. Now if I delete few nodes, so let me delete the if I delete 1, okay, so what happens, 8 will get occupied over here. So what happens is you will have 8, 16, 17 as a new node, and 18 and 19 will be a separate node. So these 2 nodes will get accommodated with this node. So now you can see 8 is combined with 16, 17, so that child is done. Now if I delete 19, what happens? So we'll see the delete 19 over here. So I'm going to delete 19. So when 19 is deleted, 17 you will get borrowed from here. So what happens is you will have 17 and 18 will form a new node. So that will get connected to the previous node. So if I draw the diagram, it will be 22 dash 18. It will not be 18, so it will be 17 dash, and you will have 8 and 16 and 17 and 19. Okay, sorry, 18. It is 18. No, okay, so you will have 18. Similarly here you will have 3 childs, 41 is to 59. You will have 22, 23 and 28, and this will be 41 and 52, and you will be having 59 and 61. So if you delete 19, so I'll write the delete over here. So if delete 19 is performed, so this will be the tree you will be having it. So this is the box you will be having. Now let us see if I delete 41, so what happens? So 52 will get accommodated to the nearby child. So we'll see it here shortly. So when 41 is deleted, 52 will get accommodated with this cell. So when it is accommodated, you can see the parent node is getting updated. So the next delete we are going to do here is we will perform delete. Which element we can delete? Okay, I will delete 16. So if 16 is deleted, what happens? So we will perform delete 16 over here. So what happens is when 16 is deleted, 8 will go and accommodate here. So you will have 8, 17 and 18. So this is the node that will be created. So the existence of this node also will not exist. So what happens is this node will be getting accommodated to the new child. So I will draw it over here. So below this, so you'll have 8, 17 and 18. So this is one leaf node you have, and next one is 22, 23, 28. Okay, this is third child, and 52, 59 and 61. It's a third leaf node. So what happens is when the existence, this will connected to this, the existence of the 22 node and 17 node will not be there. So you will have only 3 leaf nodes. So single non-leaf node is enough. So you will have 22-52. So this is the final diagram after delete 16. So let me delete another 2 more elements. So we have three elements in all the things. So let me write. So I'm going to delete from this diagram. I will delete 18, 22 and 61. So you can see 18 is deleted, 22 is deleted and 61 is deleted. Okay, so you have two nodes. So here you will get updated. So 22, if it is deleted, it will be getting updated with 23. Okay, so now this is the delete after what is the numbers we have deleted after the delete 18, 22 and 61. So this is the final diagram. Now I'm going to delete 28. So let us delete 28. So what happens when 28 is deleted? Only 23 alone there. So this leaf cannot exist. It can go to this node as well as it can go to this node. Now which node we will choose? So the difference is 17 minus 23 is 5, and here 23 minus is greater than 20 or something. So when you have less difference, you prefer with the less difference. So you will go and join with the least difference value. So so that it will be less number of splitting will happen. So you will have 52 and 59. So now this is having only one child, and you will have a node over here. Now if I delete 59, what happens? So if 59 is deleted, this node's existence not possible. So it will borrow a element 23 from here. So what happens? You will have 18 and 17 as a separate node, and you will have 23 and 52 as a separate node. Okay, and still it tries to maintain it. So search key value will be updated. Okay. Now if I delete 23, so what happens? 23 will be deleted. This node can't exist. You have a space, so it will get occupied over here. So the root node will be deleted. So the only node you will have over here is you will have 8, 17 and 52. As I said before, a root node can be a leaf node, and this is what the root node for the B tree of M is equal to 3. So I have given enough example for insert and delete in the B tree of order M is equal to 3. Thank you. We will see next example of the B tree of order M is equal to 4 or 5.